Okay, today we're going to be talking about optics, reflections, Huygens principle, and refraction. Last lecture we talked about Maxwell's equations and how they predicted that light was an electromagnetic wave. So now we're focusing on the wave nature of light. Now, I have in here just 3 slides reminding us that we have a test next week. That we have a test next week and the topics that are on the test. So it's going to be over chapters 22, 23, and 24 with the vast preponderance on 22 and 23, right? 24 was just a single lecture. It's not going to be a big part of the test. It'll be on it. You can't ignore it. But, you know, in terms of time. Okay, Sarah says, try me. Watch me. Chapters 22 and 23 were the biggies. 22 was where we were dealing with magnetism and magnetic force. So we have the different types of magnetism, ferromagnetism and paramagnetism and diamagnetism. And so I have here just the basic things about those that you need to know just knowledge-wise. Magnetic charges come in 2 types, a north and a south. And unlike electric charge, you never have a magnetic monopole. That is, you never find a single north or a single south. It's always coming together. And then Ampere's law that says that a current through a wire creates a magnetic field. And so in terms of Ampere's law and using it, you're not actually going to be required to use Ampere's law, but you may be required to know things about Ampere's law. Fundamentally, if you have a current going through a wire, it creates a magnetic field, and know the right-hand rule that goes with that magnetic field. Then we have magnetic force. Magnetic force, you have opposites attract, likes repel. If I have a magnet and I put it in an external magnetic field, so if I put a magnetic field that's pointing like this, there's always going to be a torque to try to make them align. So there would be a torque to try to make the 2 magnets align so that the magnetic field lines of the magnet and the external field match up. Magnetic field lines, remember, always go out of north and into south. What's the point of magnetic field lines, ultimately?
Show direction.
Well, to help us calculate the forces on things. That's the point of them, just like the point of electric field lines is to help us calculate the force on things. So we have these 2 equations, and then this one that is simply derived from that. So we really only have 2 equations for, this is the force between 2 parallel current carrying wires. The force for a charge moving a magnetic field, force equals QV cross B. You have to remember the right-hand rule. Anytime you have a cross product, right hand, index finger points in the direction of the first item in the cross product, middle finger points in the direction of the second item in the cross product, and then your thumb points the direction of the answer for the cross product. Now, I was going through one of the homework problems with Aaliyah this morning, and all of the questions, Anna, thank you. All the questions had for a negative charge, probably because it's usually electrons we deal with in real life. And so if you have a negative charge, your answer is negative something times V cross B, so that reverses the direction. And so you have to remember, you first find the direction of the cross product, and then if it's a negative charge, the force is opposite that. If it's a positive charge, it's that direction. Then it's fundamentally the same thing if you have a current in a wire. The direction for L vector is the direction the current is traveling, so index finger in the direction of the current, middle finger in the direction of the magnetic field, find the force. Parallel current carrying wires, R is the separation between the wires. What you have is, this is the magnetic field caused by wire 1, and then its force on wire 2 is just multiply that by I 2 times length. Since it's force per length, that's why length is on the right-hand side. So it's magnetic field times current is force per length is what we have there. But they have to be parallel for that to be correct. If they're perpendicular, the force is going to be 0 because the magnetic field is going to turn out to be parallel to the current. If I have two currents going the same direction, are they going to attract or repel? Attract. Which seems wrong because everything's been opposites attract, but for current carrying wires, parallel attracts. And you can always answer that. You don't have to have it memorized. You can answer it by saying, okay, if I have a wire and the current's going this way, magnetic field wraps around it like that. So magnetic field is going like this. My fingers show me the direction the loops go around. And then if the other wire's here, I can say, okay, at this position, magnetic field's that direction. And then if the current over here is up, I'd have the current direction cross with magnetic field, and that would be attractive. Whereas if it was down like this, I'd have the current direction cross with magnetic field, and that would be repulsive. So you can always just use the way we got that equation to determine the parallel. If they're going the same direction, they're going to attract. If they're going opposite directions, they repel. And then finally, electric motors. Now, there's a whole lot of build-up to the electric motors, so you should be able to answer a question like, what's the torque on this? But that there is the upshot equation. The torque on electric motor is N, the number of loops in the motor, times B, the strength of magnetic field, times A, the area of the loops, times I, the current going through the loops, and then sine of omega t, where omega t is the angle between the area and the magnetic field. So if it's rotating, that's why I put omega t, it's saying it's rotating at a constant rate, so things constantly changing. So that's the equation for the torque you have in an electric motor. That's chapter 22. Chapter 23 was about generating electricity from magnetism. So 22 was about force. We spent most of our time on 22, honestly. But we spent a fair time on 23 talking about the induced voltages and currents. So 23 is built on Faraday's law of induction that says a changing magnetic flux produces a voltage. Make sure you remember this minus sign should point you to use Lenz's law. The induced current is going to oppose the changing magnetic flux. So if your magnetic flux is increasing, then the induced magnetic field is going to decrease the magnetic flux. It's going to be the opposite direction as the external field. If the magnetic flux is decreasing, then your induced current is making a magnetic field that's supplementing the external magnetic field, the same direction. So Lenz's law is important for determining the direction that the current's going to flow. Eddy currents are just induced currents in a loop. So if I have a flat piece of conducting material and I have a change in magnetic flux, Faraday's law of induction says that I'm going to make loops of current flow in there. We call those eddy currents. Electric generators are fundamentally the same thing, except for we're capturing those eddy currents to use them on something. And so applying Faraday's law of induction to a coil rotating in a magnetic field, we have the induced voltage is the number of turns times magnetic field times the area of the loop. NBA, notice, was there in both the torque and the generator equation. But then we have times omega, that's the rate at which it's going around a circle, times cosine of omega t, where cosine omega t is going to be the angle between the magnetic field and the area again. The omega t is. Is that a question, Max, or just?
Yeah, is it going to be on the equation sheet?
I think it is. Something to that effect, at least, is.
You have the sine one, don't see the cosine.
Well, I put cosine here so my theta would have the same definition as it had here. So this one had sine and this one had cosine. It might say sine. In that case, it's not referenced to the angle between the two. It's referenced differently. Then mutual inductance. Mutual inductor is a transformer. And for transformers, I told you all you need to know is, first, They only work with AC. Remember I asked you the clicker question. If it's a DC voltage you connect to the transformer, what's the output? Nada, 0. If it's AC, then the ratio of the input voltage to output voltage is equal to the ratio of the number of loops on the input side to the number of loops on the output side. Now this equal sign is an equal sign for perfect efficiency. If you have no energy loss, then voltage 1 times current 1 is equal to voltage 2 times current 2. That is power in equals power out. In reality, you're probably going to have power in, voltage 1, current in, is bigger than power out, voltage 2, I2. So in reality, it's more likely going to be like that. That makes it realistic. But for your case, we're just going to assume perfect efficiency. Then we had finally, for this chapter, self-inductors, what we just call inductors. This is the physical inductance equation, how you calculate the inductance if it's an air coil. If it's not an air coil, then this just becomes mu for whatever the material is. Remember, what is that mu? It's telling you about how easy it is to magnetize the material. And a vacuum has mu 0, which is 4 pi times 10 to the minus 7 Tesla per meter ampere. Is that right? I don't remember the units. So if you have something like iron, it's like 700 to 1,000 times. It would depend on what alloy you have. Right, not, I don't know, pure iron is probably in the top end of that for the mu. And so you would have a much larger inductance if you had iron in there than if you have air in there.
You give it to us though, right?
Oh, yes, absolutely. Or unless the problem is calculate mu. And then in transient circuits, remember we did the lab and we saw the phase differences and we saw how Ohm's law related these reactances X. So X's are reactance because the inductors and capacitors store energy. They don't absorb it. This, of course, you know is resistance. And finally, Z is the impedance. It's combining anything that's making it hard to put current through.
I thought we weren't doing anything on transient.
Like what?
I thought transient circuits weren't going to be on.
Right, transient circuits aren't on the test. I have it on there, but they will not be on the test is a correct statement.
What ROC currents are?
Yeah, we did a lab on it. So, and finally, chapter 24, we had Maxwell's equations. Important things for you, Gauss's law for electric fields. You already know that in other terms that the electric field lines go out of positive into negative. Right? It's not a new thing. Faraday's law of induction. In terms of this chapter, a changing magnetic flux produces an electric field. And Ampere's law, a changing electric flux produces a magnetic field. And so because of those two relationships, then it supports electromagnetic waves. Yes.
So with this chapter, what is this good? Is any of this going to show up in the synthesis or application problems?
Not chapter 24, no.
Okay, that's all going to fall under the knowledge.
Under knowledge, yes.
Okay.
And remember, what did Maxwell do that was so important? He reduced the number of equations. We didn't actually talk about this. We got down to here. Heinrich Hertz is the person who experimentally showed that Maxwell's prediction that light was an electromagnetic wave was in fact correct. Heinrich Hertz studied to see if electromagnetic waves had the same reflection properties we're going to study today, had the same refraction properties we're going to study today. And they did. And so he concluded, yes, light must be an electromagnetic wave because they have the same properties in terms of reflection and refraction. And then this here, of course, you know this one was important. The electric field, magnetic field, and velocity are all mutually perpendicular for the electromagnetic wave. So if you know the direction of the wave, you know the electric magnetic fields have to be perpendicular to each other and perpendicular to that wave. They could be changing orientations, but they have to be perpendicular. And I should have emphasized that equation. If I had emphasized that equation, I would have had a homework assignment due today. But I didn't, so we don't.
So we're going to use that equation on the test?
We will not. We'll just save that for the next test because the next test is optics. And that's the speed at which an electromagnetic wave travels. So I'll do a little more review again on Monday, but those are the things to be preparing on. It was hard stuff, right? And it's easy to get bogged down. There's so much stuff here. But after going through it, when you come back, the actual outcomes, the things we have to do with it, aren't as big. The ideas are the big thing that are hard to put in your brain. Claudia.
So for the test, is chapter, what we just read, chapter 25, also part of it? Or
No, chapter 25 is not on the test.
So 22 through 24?
Yes.
Okay.
With the vast majority, 22 and 23.
Do you mind going back to slide 20 for chapter 24?
This is all gonna be on Moodle, correct?
Yeah. All right. So talking about reflection and refraction. We're talking about light behaving as a wave here. And so when you get to like Huygens' principle only applies if you have a wave. The first things we're going to learn, it doesn't matter if it's a wave or a particle. And I have to point out whether light is a wave or a particle is actually a big thing. Back in the day, you always thought that light was like tentacles coming out of your eyes. But then we had a particle theory that says light is like particles. It's like BBs. And those BBs come and hit your eye and you detect something. But then we had Thomas Young, who did some experiments that showed that light had properties that only a wave can have. That light would interfere with itself, which we'll get to later. And so then the whole world shifted. Oh, light is a wave, it's not a particle. And it went that way until Albert Einstein said, no, light is a particle. But we already had a definitive experiment, a Nobel Prize winning experiment that said light cannot be a particle. Remember, when you're doing experiments, you disprove things. You don't prove things correct. And so there was that experiment Thomas Young did prove that light couldn't be a particle. But then Einstein proposed an experiment that we're going to do that proves that light can't be a wave. And so we're left in a real quandary. What is light? And the conclusion that we use, to me, is very unfulfilling. We say that light is both a wave and a particle, and depending on what you're studying, you should evaluate it with one or the other. Yeah, exactly. So right now, we're examining things through the lens of a wave, and then after a couple chapters, we'll shift to looking at it as a particle. So getting started.
Sorry,
Yes.
I know we have a lot of stuff to get through, but can we go back to the part where you said we used to think that light was tentacles coming out of your eyes?
What about it?
That was like a thing?
That was a thing. It was a thing according to an optics book I had in the long ago. You know, like the Greek philosopher times.
Wild.
I couldn't tell you who it was that had the tentacle theory. It stuck with me because it seems so bizarre. I always say that's scary because if you go like this, you could blind yourself, which is obviously why John Cena does this. You can't see him because he's cutting the tentacles, right?
Oh my word.
I don't know anything about John Cena. I had to ask somebody, what's that supposed to mean? Okay, so light. Most objects are not sources of light. I look at Maxwell. Maxwell is putting out some light but I can't see it. It's in the infrared spectrum. If we use night vision goggles, then we can see the light he's giving off. But right now I'm not seeing the light he's giving off. What I'm seeing is the light he's reflecting. It's like the Bible says, we need to be reflectors of God. Max is reflecting the light in the classroom. So light from the classroom hits him, comes to my eye, and I see that light. So most things are just reflecting light. They could be transmitting light. So like a window, the light transmits, goes through. Or they could be absorbing. And honestly, we're absorbing a lot of the light that hits us, right? A lot of the light that hits us comes into us. Now, I use Max as an example. Max is absorbing more light than I am. How do I know this? Darker. If things are darker, they're absorbing more light. If you look at David's shirt, it's absorbing more light, so it's darker, so it's absorbing more light. But cart before the horse. Max, question.
You're saying infrared window can see what we give off?
Yes.
It's not like heat though?
It's radiation, and heat has three forms: radiation, conduction, and convection.
Alright.
And so it's one of the three forms of heat. So when we look at things, we just see the light that's reflected. If I look at Jenna's sweatshirt, I think it's a sweatshirt, it's something like a, let's say, aqua colored shirt. What that means is it's reflecting certain colors. It's reflecting green and blue, so I see it as that color, but it's absorbing red. Now, if I look at Max's shirt, it's doing just the opposite. It's absorbing green and blue and reflecting red. Now, I'm only using three colors. I'm only using three colors because we have effectively three different colors we can see with our eyes. We call those the primary colors of light: red, green, and blue. And so I usually just talk about light in those terms. But in reality, light is a spectrum ranging from, well, you probably learned, Roy G. Biv, ranging from red up to violet. And we talk about this spectrum, and we'll talk about the spectrum later more carefully, but we generally refer to it with wavelengths, which will be defined on like an upcoming page. 400 nanometers is red, and 750 violet. 750 nanometers is red. And so that's the range we can see. Now, the range that you're giving off with your body is in the micrometer range. And so that's why we can't see it. The range your body is giving off is over here. Okay, so back to things that are on the slide. Yeah.
So we're bioluminescent, but like our eyes aren't equipped to like see the amount of light that we give off. Would it be possible for a being with like more sensitive eyesight to be able to see the bioluminescence of humans?
Yeah.
Wild. Cool.
It actually wouldn't be termed bioluminescence, I don't think, but it still is what you're talking about. It's a living thing giving off light.
Yes.
Okay, so let's talk about the wavefronts and rays. We use at this point a ray model of light. Anyone who spent a little time in the geometry class had to learn things like line segments. Line segments have a starting and an ending point, right? And then you had lines. Lines have no starting or ending point. And then you have something in between, rays. Rays have a starting point and no ending point. When we talk about the ray model of light, we're saying that light is traveling in a straight path with a starting point of wherever you started and no ending point unless it hits something. Of course, if it hits something, that becomes a line segment. But nobody wants to talk about the line segment, so we say ray. So we have light traveling out as rays. And we have the wavelength, and you'll remember this from sound. If I have position on this axis and displacement on this axis, then how do I define the wavelength? Yeah, the wavelength is the distance for it to repeat. Now, the trickier question than that, we didn't have a lot of people jumping at the response there, so I'm just going to write it, is the symbol for wavelength. Oh, well. Okay, so y'all remembered that. The symbol for wavelength is lambda, the Greek letter L for length. So if we have rays traveling, one of the things we like to do is talk about wave fronts. It's the front of a wave. Well, the front of a wave, if I have a bunch of waves traveling, we talk about the wave front as being the place where all the waves are at a maximum. So here's my wave fronts, separated by one wavelength. So here's a picture of waves on water. Now, let me go back. That was not back. If this is light wave, what is the displacement? What's being displaced? Like if it was a sound wave, it was easy. It was the air molecules moving, right? If it's an earthquake wave, it's the ground moving. What's being displaced with a light wave?
That's a dark matter.
Funny. Sorry, what did you say, Aaliyah? Oh.
I asked if it needed anything. In space?
It does not. It does not. That's an important thing that I haven't brought up yet. But what is oscillate in an electromagnetic wave? Electric field and magnetic field. They're both oscillating. So this displacement could have been electric field or it could have been magnetic field. They oscillate together, so either one would be perfectly correct. Usually we default to electric field. So I'm usually just going to say electric field. But if I said magnetic field, it would be perfectly correct just the same. So here, this is a water wave. And so there I'm trying to draw the peak of the water wave. Got off one because when you go around the corner, you have to shift from bright to dark. There's the peak of a wave. What direction is that wave traveling? Outward, right? There's no other answer that's a good answer. Its velocity is like this, outward. And you have the wave fronts are the places where you have the high points. So I just drew a circle for the wave front for that wave. And then I could draw a circle for the wave front that's one further out. And I'll just do half of it here. Well, I missed, but you see what I'm talking. And I could have done for one further the other side. And what's the separation between those wave fronts? The wavelength, lambda. So if I have a wave that's going out in two dimensions, like what we saw here, it's a circular wavefront, right? What's going to happen to the energy per unit length of that wavefront? As I go farther, what's happened to the circumference? It's increasing. Circumference is 2 pi r. So the bigger the radius, the bigger the circumference proportional to r. But if I only have so much energy and spread out over a bigger length, what happens to energy per unit length? It goes down, proportional to 1 over r. Now, if it's a spherical wave, which is basically what happens if I turn on a light bulb, the light goes out in all directions as a sphere, then the surface area for a sphere is 4 pi r squared. And so the energy is distributed over the area of that sphere. And so the energy per area per time we call the intensity, is going to drop off as 1 over radius squared because it's being spread out. And so for a spherical wave, it drops as 1 over r squared. For a circular wave, 1 over r. But then there's the planar wave. How much spreading do you have if you have a planar wave? If all the lights go in one direction? Yes, the answer is none. Hence, the intensity for the planar wave stays the same. So if I have a laser beam, that laser is sending out a planar wave. It's all going the same direction. And so the intensity of the laser beam should stay pretty much the same and not drop off like it would with the light bulb. Except for, of course, air does some absorption and that kind of thing. And in all cases, the wave fronts are separated by a wavelength. This picture here is trying to show a 3D version. Very tricky. So now I think I have my first woo clap question.
Oh, let's do this.
I think it's .com. Yeah, .com.
.com/PHYS1.
And it's now open for you to answer. What is the spacing between adjacent wavefronts? That's the one next to the next one. You know, not skipping one.
Why do we get so big?
Because Microsoft Word makes 1/2 into a single character, but it does not make 3/8 into a single character. I was short on time, or I would have gone through the equation editor and made them all the same. Okay, we have 7 answers. A. All right, everyone's answered. So we had 5 people that said half a wavelength, 1 that said 1/4, 0, 0, and 4. So let's go back and look. What was the space between adjacent wavefronts? 1 wavelength. It's not going from peak to minimum. It's going from peak to peak for the wavefronts. And you might ask, why is this important? Because we're going to use it in analyzing reflections and refractions. So if I have light coming into a surface, what are the things it can do when it hits the surface? Okay. Now she said refract, she said absorb. I'm just going to go with it can be reflected or it can be transmitted, which includes refraction, or it can be absorbed. Right? It's going to do one of those things. It's going to go through it, it's going to reflect off of it, or it's going to stop. So what we're focusing on here is reflecting. So what we're going to have is a surface that is highly reflecting. Something that's going to reflect electromagnetic waves. So we have the lights coming in. The blue is showing the light. So these are the light rays coming in. The black is showing the wave fronts. So what's the separation between the black lines? 1 wavelength. Not a half. 1 wavelength. Separation between the blue lines is immaterial. That's just randomly chosen for the picture. So it comes in and reflects. How does it reflect, you ask? Well, we can explain this with Huygens principle. We can give a good scientific derivation for it. But the answer is simple enough that we prefer just to give you the answer. So I draw a line that is normal to the surface. Every time I say normal, I have to remind you, normal means the direction that is directly coming out of the surface perpendicular to any line that you draw on that surface. You draw any line, if it goes through the point, the perpendiculars to all of those lines are going to be the normal direction. And then we just measure the angle between our incident ray and that, and we call it the incident angle. For reflections, it's not super important, but for later on, it is super important, so I emphasize it now. It's not the angle between the surface and the incident means incoming, in case that's a confusion point. It's not the angle between the surface and the incident ray. It's the angle between the normal to the surface and the incident ray.
Can you give an example of this?
Sure. This gives me a nice normal to the surface. So if I have light coming in like this, the angle of The angle of incidence is this angle here, not this angle here. And then we do the same definition for the reflected ray. So the angle of reflection, and you actually have to go to the fourth letter to make it unique from refraction. The angle of reflection is the angle between the surface normal and the reflected ray. And then we get the law of reflections, which is the simplest law you will learn. Theta incident, actually I should put a C there, is equal to theta reflected. You already probably knew that. You know that from practical experience. If there's a mirror up here and I want to see, I just keep using Max as my example. If I want to see Max, I look here so that this angle here matches that angle there to see him. I don't look over here and expect to see him in a mirror that's in the front. Right? So we have a practical experience for this. So it makes a lot of sense. Angle of incidence equals angle of reflection. So here is showing a bunch of parallel rays hitting a surface, reflecting off. We call this kind of reflection a specular reflection. Another name for specular reflection is a mirror-like reflection. So mirror-like reflections, specular reflections are simple. Angle of incidence equals angle of reflection. And how do you measure that angle of incidence and angle of reflection? From the normal to the surface. But then there's another kind of reflection, diffuse reflection. A diffuse reflection occurs when you hit a rough surface. And when I say a rough surface, I mean a surface that is rough on a microscopic level. This tabletop is rough on a microscopic level. It feels smooth to the hand. It looks smooth. But on a microscopic level, it's rough. And so, rough surface, you have the direction of the surface normal is random directions pretty much, right? The surface normal here is pointing up like this. The surface normal here is straight up. The surface normal here is out like that. And so that means the directions of the reflections, even though these are all parallel incoming, the directions of the reflections are pretty much randomly distributed. So that gives you a diffusion. It spreads out the light. Whereas the specular reflection, it was a reproduction of the light.
Can you go back one slide real quick? Okay, thank you.
So now, how do you tell the difference in a specular reflection and a diffuse reflection? Here's my easy answer. When I look in a mirror, I'm seeing a specular reflection. And when I look in a mirror, what do I see? I see myself. But if I look at the tabletop, I don't see myself because it's being diffused. So if you see an accurate reflection of something, it must be specular. If you don't see an accurate reflection of something, it must be diffuse. It's pretty easy to determine. So here is what defines smooth versus non-smooth. If the size of the pits and holes in the reflective surface are small compared with the wavelengths, then you get specular, then it's smooth. If the sizes of the pits and holes are larger than the light wavelength, then you get the diffuse. Now here's a good practical example. These days you don't see the big ugly satellite dish very often, but you used to see them all the time in people's backyards. And sometimes you'd have a solid dish, and sometimes you'd have a wire mesh dish. Did you ever see those wire mesh satellite dishes? Okay, Aaliyah did. Thank you for seeing one. I mean, we're moved far enough away that this is not an everyday experience. The wire mesh works because you're dealing with waves that have wavelengths that are measured in, like a foot or more. And so if your little pits, the holes between those wires is small compared to a foot or more, then it looks like a smooth surface and you get a nice specular reflection. If you're looking at light waves, you get a diffuse reflection for sure. Those are way bigger than the wavelength. So that's why it was possible to make a satellite dish that was a mesh pattern so wind could blow through it instead of a solid shape. All right. Here is our second clicker question. When you look at the face of a friend, any friend, we're not picking on anyone, what kind of reflection do you see from his or her skin? A reflection of love. Very good. Got 7 answers so far.
I don't think you'll get my answer because
Can't blame it on the computer this time.
well, I'm like trying to like take notes on one note, so like I have to like set it up.
I'm especially glad, by the way, that you're no longer experiencing exploding
So like
cables and
Yeah.
transformers.
Me too.
you're
I am with
the
you.
light
That is
is
important.
bouncing
Yeah,
off.
it is. Okay, we only had 8 people answer, but we'll just go with that. We had 2 that said specular and 6 that said diffuse. What was the question I gave you to determine which one's which?
Can you see your image?
Do you see your image when you look in your friend's forehead?
Yes.
No.
Okay. Sarah says that they have a really greasy forehead. You do.
Ew.
If they have a really greasy forehead, you do. Why? Because that oil is filling the holes and the oil is giving you a smooth surface. So you get a bit of a specular reflection off of somebody with an oily skin, which is very natural. We shouldn't be embarrassed about it. Just, don't want anyone to be like, So the general action is diffuse. Generally, you don't see yourself reflected in somebody's face. Now, if you look at the eyeball, then yes. Some people's teeth.
Whoa.
Okay. So we know the difference between specular and diffuse reflections. Well, 6 of you know the difference. Hopefully the others picked it up after the question. So here's my actual picture saying the angle of incidence equals angle of reflection. We've already covered this. Just making sure you see a nice picture, the normal to the surface, angle of incidence, angle of reflection identified. Very important question. How is the angle of reflection measured? By eyeballs?
There's this really close one that you can measure like the angle of your lips. Okay. Boom.
You're right.
I know.
So is the other person who answered. That's how I knew.
Am I?
Only 2 people, well, now 4, and they're all right. 5, they're all right. I'm going to stop answering now because if somebody answers wrong, they'll know.
That's them.
Yeah.
Sorry.
Lord, is it I?
I thought
Apparently so. Okay, we got 8 answers this time. We're getting, well, actually, that's how much participation we had last time.
so. Let's go.
Woohoo, 9. 9, yeah. One more person's engaged. Give it the last 5 seconds, see if the last person's in. Okay, so this time we had 2, 1, and 6. So 2 people said incident ray to the reflected ray. 1 said angle from the plane of reflected surface to reflected, and 6 said from the normal. So let's go back to the picture. 1 person said this. 2 people said, 2 people said this. And 6 people said that. It's the angle from the surface normal. Remember, I can't emphasize enough. This is important. Angle from the surface normal to the reflected ray. This right here, by the way, would be the deviation angle. That's measuring how much it totally changed in direction. So that was the correct answer, the 6. So the majority was right. So here are formalized rules for that law, or for measuring the angle of reflection. First of all, you have the angle of incidence equals the angle of reflection. and the reflected ray lies in the same plane as the incident ray and the surface normal. That is, you don't have the incident ray coming in like this and the reflected ray going out like that. It's going to be in the same plane like this. No one probably would have made that mistake, but it's just codified here, so it's absolute. Steadily?
Will we have homework?
Yes, you'll have homework. And what?
Due Monday?
What things will be over?
Over the laws of reflection?
Not after calculations or
No, there'd be calculations involved.
what calculations?
Angle of incidence equals angle of reflection. Or looking here at a more complicated case. This young lady is looking at her reflection in a mirror. What's the first thing you notice that seems odd about this picture?
Her right foot's darker. Her left foot's darker than her right foot.
That actually is a lighting issue. The back foot is in the shade of the front foot.
Why is the normal surface coming out at the bottom of the mirror instead of somewhere else on the mirror?
It depends on where she's looking, what direction the normal is. The normal is going to be like this everywhere.
Right. And so it just depends on where
Depends on where she's looking.
she's looking. Okay.
Okay, what other things stand out to you? If it's inappropriate, don't say it. What other? There's something that to a lot of people seems a little surprising here.
Is it
Her
two
feet.
incident rays?
Her mirror is so much higher than her feet, but it's showing her feet.
Okay, that's what I was looking for. The mirror is so much higher than her feet, but showing her feet. To look at her feet, she has to look down so that the angle of, so light is coming from her foot. Light from her foot is going in all directions, right? But the only one that's going to get to her eye is the one where the angle of incidence is equal to the angle of reflection.
Is that why, like, so if you stand close to a mirror that's like, you know, at your torso level, I guess, if you're close to it, you're not going to see it. But when you step back, you can eventually see your whole body.
That's something I'm going to contradict, but the reason is because we're assuming here for physics that your entire body is straight below your eyeballs.
You're going to contradict my last statement, but it's true.
Right. For what I'm saying here, we're assuming that her eyeballs are straight above all the rest of her body. Obviously, her body, some parts like the neck is further back, some parts are closer, but we're just assuming that it's all straight up and down. So the fact is, you know, your eyeballs are probably in front of your ankles. And so with your eyeballs being in front of your ankles, what I'm going to say is slightly different than that reality. So that's what I meant by I'm going to contradict it here because we're making that assumption.
That works. When I step back, I go down.
So to see her feet, she only has to look halfway down because the angle, if you just do triangles, we have similar triangles. We have, this is a right angle, and then we have angle of incidence and angle of reflection are the same, and this side of the triangle is the same. So she has to look down to halfway between her eyeballs and her feet to see her feet. So a full body mirror only has to be half of your body height. You have to have the bottom of the mirror at the position halfway between your eyeballs and the floor, and the top of the mirror position halfway between your eyeballs and the ceiling. Or excuse, not the ceiling, the eyeballs and the top of your head. Now, unfortunately, they tend to put these mirrors so the top of them is about even with my nose, and the bottom of them is down mid-thigh, and so I can see from, chest down, which is a pain if you're going to be doing things like shave in a mirror.
Oh, I don't want to do that. But I also think it's
Last thing, multiple reflections and measuring the deviation. So here I have an example of what we call a corner cube mirror. It's a right angle. My incident light is right here. This is incident. And so you have two reflections. The first reflection causes this much change from straight. The second reflection causes this much change from straight. And so the goal of a problem like this is to calculate what's the angle between the incoming and the outgoing. And so the way to solve this is through geometry. Through geometry, you know this angle is equal to this angle. And you know that these are right angles, so you can calculate what this is. And then you have what the total deviation is, 2 times that. And then you come here, and once again, you know this angle is the same as this. So then you can calculate what this remaining is, and that's, of course, the same. So you do geometry, and I would do it completely right now, except for it's time for us to go.
We're not going to have a question like this on the homework. Right?
You will have a question like this, and you can wait until class on Monday when I will finish this problem up, and then you will have, if geometry is not your hot thing, then seeing me work it out will make it easier for you. So I will work this out at the beginning of class.
Okay, thank you. Now he's talking to me.
I was not talking to anyone.